Hello and welcome to part 9 of the series on computer networks. I hope you have watched the previous parts of the series. If not, you can always check out, the links are given in the description. So today's topic of discussion is error detection, and there are various methods of error detection. So out of that, we'll be discussing single dimensional parity checking today. So let us try to understand what error means. So let's say we have two nodes, node A and node B, and data is being sent from node A to node B. Let's say the data at node A is 101. We need to send 101 from A to B. If it is received, and this 101 will go through this transmission medium, this is called the transmission medium, and if it is received in the form 101, then we say that the transmission is successful and it is a correct transmission. But if you intend to send 101 but it is received at 011, that means whatever we are sending, we are not receiving that. We are receiving a different bit. See here, this 1 has become 0 here, this 0 has become 1 here. So here we say that transmission is not successful. So what is error? So if data is not received in the form in which it is sent, we say that an error has occurred. So for example, if you see in this example here there are 8 bits of data. If you see the second last bit, is 1. If and while going through the transmission medium, this 1 has changed to 0. That means an error has occurred. This is the form in which we send the data, but we have received the data in a different form. So as we have received the data in a different form, we say that an error has occurred. Now why error occurs? The data while going from the source to the destination, it needs to go through what? It needs to go through various transmission medium. So while going from source to the destination, in the transmission medium, the data might be corrupted. So for reliable communication, these errors must be detected and corrected. So if the data which we are sending is not received in the form in which we are sending it, then it is of no use. So if errors occur during transmission, we must be able to detect it. So there are various error detection strategies. Out of these error detection strategies, one of the strategy is single dimensional parity checking, which we shall be discussing in today's part. So let's go to the types of errors. So basically there are 3 types of errors: single bit error, multiple bit error and burst error. Let's go to these errors one by one. So what is single bit error? If only one bit of the transmitted data got changed from 0 to 1 or from 1 to 0, it is called single bit error. For example, let us consider the data 10110111. While going through the transmission medium, this data has changed to 10110101. So the other bits are fine, only the second last bit is corrupted. That means there is error only in one bit. The data units, these are called individual data units, are called bits. So here we are getting error only in one bit. As we are getting the error only in a single bit, this is known as single bit error. Next we go to multiple bit error. So by the name only it is clear that here we will have error in more than one bits, but if two or more non-consecutive bits of data get changed from 0 to 1 or from 1 to 0, it is called multiple bit error. For example, if you see the data at the sender, it is 100101110, and while it is being received, we see that it is being received as 1011010. We see that 2 bits are corrupted and these 2 are non-consecutive bit. Do you know what is the meaning of consecutive and non-consecutive? I guess yes. Consecutive means which are together. For example, 100, if it gets changed to 111, these 2 are consecutive bits. These consecutive bits are changing. But if 100 gets changed to 0, 0, 1, this bit has changed and this bit has changed. These two are non-consecutive bits. Non-consecutive means they are not together. So if two or more non-consecutive bits gets changed during transmission, we say it to be multiple bit error. The last type of error is burst error. So in case of burst error, two or more consecutive bits gets affected. For example, in the sender, you can see that 101 got changed to 010, and these three are consecutive bits. If consecutive bits gets affected during transmission, we say the kind of error to be burst error. Now we'll go to the various error checking techniques because errors are undesirable. So the first error checking technique is single dimensional parity checking. The second is two dimensional parity checking. The third is CheckSum, and the fourth is cyclic redundancy check, popularly known as CRC. As per the CBSE syllabus, we need to study number 1, 2 and 3, and in this part of the video I'll be discussing single dimensional parity checking. So let's go to single dimensional parity checking. So before that, we need to know about a term known as parity. So what is parity? Parity refers to an additional bit added to the actual data. So in case of single dimensional parity check, blocks of data from the source are subjected to a parity bit. So let's see what parity means. So let's say this is the data which we need to send. There are how many bits? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 bits of data, and it is known as the data unit. This is the actual data which needs to be transmitted. If along with that data we add an extra bit, let's say this one is the extra bit which we add to this actual data. This extra bit is known as the additional bit or the parity bit. So if along with the actual data we are adding something extra, adding an extra bit, it is known as the parity. So for example, if the data to be sent is 1001, but if we are sending it as 1001 and we are adding something else like 0, adding an extra 0, this is the extra 0, so we say this 0 to be the parity. Instead of 0 we may add 1 also, then also it will be known as parity only. So hence the total number of transmitted bit will be 9 bits. So 8 bits are the original data and 1 bit is the additional parity bit. Next, we go to ways to generate single dimensional parity. So there are two ways in which single dimensional parity can be generated. First is even parity. In case of even parity, the total number of ones transmitted must be even. So in case of even parity, if we are following single dimensional parity check with even parity, our aim would be that the final transmitted data should always be even. If we are using odd parity, then it should be clear that our final transmitted data should be odd. For example, suppose we want to send 101 along with the parity, and suppose we are using even parity. So here the number of ones are already 2, that means it is already even, so we will keep the parity bit as 0. Only then the number of ones will be even. Let's say we are using odd parity technique, then what we will do here, number of ones is even, so our aim will be to make it odd and then send, so we'll add the parity bit as 1 in this case. So it will be more clear when we go to the sums. So let us go to the steps for even parity. So there will be two parts, one at the sender's end, some parts will happen at the sender's end and some parts will happen at the receiver's end. So the first step is we need to count the number of ones in the actual data unit. Actual data unit means the data unit which needs to be sent from the sender to the receiver. For example, if the data transmitted is this, let us count the number of ones here, 1, 2, 3, 4, 5. Here we have 5 number of ones. So our first step is to count the number of ones in the data unit. So the second step is add an extra bit, either 1 or 0, based on the following. So here we need to add a parity bit. So the parity bit would be either 1 or 0. How to decide whether we are will be adding 1 or 0? It will be based on whether we are using even parity or odd parity. So for odd, so here we are using even parity. So our final aim would be that whatever data we will be sending, we want to send data in even form. So if there are odd number of ones, as in this case, we will add the parity bit as 1, because if there are odd number of ones, how can we make it even? By adding one more one. So here number of ones are 1, 2, 3, 4, 5. So how to make it even? By adding the parity bit as 1. So if I add the parity bit as 1, then the number of ones will become 6, and therefore it will become even. But for even number of ones, so if the data bit is already even, as in this case we have 1, 2, 3, 4, 5, 6 ones. If the data unit to be sent is already even, then how can we make it even? By adding the parity bit as 0. So these are the steps which will happen at the sender's node. It will be more clear when we take an example. So at the receiver node, what we need to do, from the received data, whatever, so this is the data to be transmitted. So and we will get some data in the receiver's end. From the receiver's end, we need to exclude the parity bit and once again determine the parity as has been done in step 2. Now if the parity bit which is received and the parity bit which is recalculated is the same, then we will accept the data, otherwise we will reject the data. So if we will use odd parity, the steps will be the same, only the thing which will change is here. So for odd parity, our aim will be to send the data with odd number of ones. So here if we have odd numbers of ones, we will add 0 as the parity bit, and if we have even number of ones, we will add 1 as the parity bit. At the receiver's node, what we will do? We will take the data which is received, and from that we will keep the parity bit aside and recalculate the parity bit as has been done in step 2. And if the calculated parity bit and the received parity bit is the same, then we will say that the transmission is successful, otherwise there is some error in transmission. Let us try to understand it with the help of an example. So pay attention here. So this is a question. Let us consider two sample data units 1011, 0111 and 1100, 1011 at the sender node. So these are the data, these two are the data which needs to be sent, which gets transmitted as this and this. So at the receiver's end, we have received the data as in this form. Check the correctness in transmission using single dimensional parity checking. We need to check whether the data has been transmitted correctly or incorrectly using single dimensional parity checking. So we as human can just look at the data and say that whether the data has been received in the correct form or not in a correct form. But for computers to know the same thing, some algorithm should be there. So the algorithm which is used here is single dimensional parity checking. So here, so what are the data at the sender's end? It is this 1011, 0111. You can match it with the question here. So here, what is the number of ones? 1, 2, 3, 4, 5, 6. The number of 1 is 6. So that means we have even number of ones. Here, how many number of ones we have? We have odd numbers of 1. There are two chunks of data. So let's say the first is case 1, the second is case 2. What was the second step? The second step was to add an additional bit which is known as the parity bit. So for case 1, so we are using even parity. So our aim will be to send the data with even number of ones. So the number of ones in case 1 is already even. So we will add a 0 as the parity bit. So for the case 2, the number of ones is 5, that is odd, but we are using even parity. So we need to send it as an even number, the ones as an even number. So we will add 1 as the parity bit. So after doing it, it will be sent through the transmission medium. So after sending through the transmission medium, at the receiver's end, it is received as, see the question, 1010011, which is case 1, and 11001011, which is case 2. So in case 1, we see that number of ones is 5, that means odd, and in case 2, we see that the number of ones is 5, which is odd, but we are using even parity, so our aim would be to make the number of ones even and then send it through the transmission medium. So in case 1, so what we will do, we will recalculate. So try to remember the steps at the receiver's node. What we will do, we will recalculate the parity bits. So here the number of ones is odd, so we will add one more one to make it even, and in the second case the number of ones is odd, so we will add one more one so as to make it even. After that, what we will do, we will match the parities at the sender node and at the receiver node. So parity bit at sender node in case 1. What is the parity bit at sender node in case 1? It is 0. What is the parity bit in the receiver's node in case 1? It is 1. So see, parity bit at sender node in case 1 is 0. Parity bit at receiver's node in case 1 is 1. So here, are the parity bits matching? No, they are not matching. So since the parity bits do not match, we say that there is some error in transmission. Let's go to the second chunk of data. In case 2, what is the parity bit at the sender's node? 1. In case 2, at the receiver's node, what is the parity bit? It is 1. So parity bit at the sender node in case 2 is 1. At the receiver node also, the parity bit is 1. Since the parity bits match, therefore the transmission is successful. Now you should go back to the steps and now it will be very clear to you. So the entire thing has been given here as a flowchart. So we'll take the data and then add the additional bit. That means we'll calculate the parity bit. These things will happen at the sender's node, and then data will be sent along with the parity bit through the transmission medium. After that, we will count the number of ones in the received data, excluding the parity bit. So while receiving, we will receive the parity bit also, but we will exclude the parity bit and count the number of ones and recalculate the parity again. Now, if the parities of the calculated at the sender's end and at the receiver's end match, then we will drop the parity bit and accept the data. If it matches, obviously we will accept the data as in case 2. But as we have done in the previous sum in case 1, the parity bits did not match. If the parity bits does not match after following these steps, we will reject the data and request the sender to retransmit the data. Why retransmit the data? Because there were some error in transmission. So let's go to the advantages of single dimensional parity checking. It is a very simple mechanism because here we need to just add the parity bit, and it is an inexpensive technique. Next, let's go to the disadvantages. It can detect only single bits error, and single bit errors are rare. So when data is being sent from sender to receiver, generally errors do not occur only in a single bit, or errors most often occur in more than one bit. So if error occurs in more than one bit, it is the single dimensional parity checking will not be able to detect it. And the second disadvantage is that it cannot detect errors if two bits are interchanged. So here, see, the data is sent as the 11001011. This is at the sender node. Okay, so let's say we are using even parity. So how many ones are there? 1, 2, 3, 4, 5. We have 5 ones. So how to make it even? By adding the parity bit as 1. And at the receiver's node, the data is corrupt during transmission and the data has been received as 100111011. See, this 1 has changed to 0. That means there is an error in this bit, and this 0 has changed to 1. That means there is an error in this bit also. But see, 2 bits has interchanged. 1 has become 0 and 0 has become 1. So let us recalculate the parity here. So the parity will become now what? 1, 2, 3, 4, 5. We have odd numbers of 1. So the parity will be 1. So as per the single dimensional parity check, what we will say? We will say that the transmission is successful, but is the transmission actually successful? No, the transmission is actually a failure. So as the transmission is actually a failure, we say that this technique is not very effective. So since this technique is not very effective, we need to go to the next technique, which is two-dimensional parity check. So that's all for today. We'll be discussing two-dimensional parity check in the next part of this series. Thank you very much.